place learning. All right. Now I'll give control over to you so you can start the workshop.
And if you wanted to interested in the following along,
Yes.
GitHub in the workshops directory. In theory, like you could either create a new Jupyter notebook and code it up along with, depending on what you want to do, but some of the stuff is kind of a pain, and there is a file that's got some helper functions. So
Gotcha.
it's probably beneficial to just download the directory.
All right. Yeah, I'll do that. Is it on it's on the main branch too?
Yeah. For anyone, I guess I'll do it on the, I'll go to the S24 UMISH GitHub. So you go here, go to documents, workshops, quantum computing, and then these are all of the functions. If you want the link to the presentation, this is just like a text file that you can, the link is here. Anyone that has the link can view the presentation. It's available if you're interested.
So, and the good thing with this format too is like, so I already have the documents repository on my computer, so I can just update it and I get all the new like workshops.
Cool. I need to get mine figured out better. Okay. Yeah. But anyway, so there's the three files. The helper functions then will do two separate methods.
So is okay. So it's two separate things. Got it.
But yeah, I've got some like background info as well, because I figured most people wouldn't have a super strong quantum computing background.
Yeah.
Sorry, I was just gonna give a little bit of background as well.
All right.
But I'll let you like get that out.
Is there any special like packages you need?
Yeah, but it's just a single pip install, and right in the top of the Jupyter notebooks, it has the install commands.
Okay. Cool. Yeah, I'm ready when you.
Yeah. So yeah, all the stuff is just Qiskit and Qiskit there. This one should be installed automatically. It should just be this first one, but I have it here just in case it's installed.
Yeah, sometimes it can be funny.
Anyway. Okay, so today we're just going to go ahead and talk about an introduction to quantum computing and quantum algorithms. So to begin, I'm just going to give a little bit of background in terms of why people are excited about quantum computing. And the idea is that it can give us this massive speed up compared to classical compute power. So if you compare to how classical computers work, this is at the top left with the binary vectors section. Depending on the size of your transistor, every single piece of information that you want to process is going to be encoded as a binary vector. So this is just a vector of numbers, and the information is coded into these J1 up through Jn. So if you want to encode n pieces of information, or if you want to manipulate a vector of length n, you need n classical bits in order to process that information, where each of those j's is either going to be a 0 or a 1. So you end up with this length n bit stream to manipulate a length n vector that you're trying to deal with. And you can talk about how you would encode, real numbers into binary, that kind of thing, floating point numbers, that kind of stuff. But in contrast, quantum vectors or Q vectors are exponentially larger, because the idea is if you have n qubits, and what this Q vector section is for an n qubit system, each possible state of that system is going to be a length n bit stream. But there are actually 2 to the n different possibilities, 2 to the n configurations that this state can take on. And those configurations are represented by these a coefficients, a0, a1, all the way up to a to the 2 to the n minus 1. So what you get here with n qubits, instead of an n vector that you can now manipulate, you can now process information that lies in this 2 to the n size state space. So what this gives us is that for an equal number of bits versus qubits, you get an exponential advantage in terms of the size of system that you can manipulate. So what this means is that as we get chips that have more and more qubits on them, quantum computers with more processing power is what I mean by that. the quantum compute power will exponentially outstrip the classical compute power because it will grow exponentially with the number of qubits as opposed to linearly as classical compute power grows. So eventually, as quantum computing continues to advance, the idea is that we'll be able to take advantage of this exponentially sized state space to be able to solve problems that are intractable on today's classical computers. Now, as a note, this is all very well and good, but there are some caveats here. There's some rules that we have to obey. It's not just for free. And in fact, quantum computing is not going to apply to every problem. We have to look for good problems that have a good adaptation to find some sort of a speed up by using quantum computing. So in terms of these A coefficients, what we have to remember is that upon measurement, the system is going to collapse to configuration J with probability A sub J magnitude squared, where these A sub J are complex coefficients for each of these state vectors. So what this means is that you can think about this A vector, this length 2 to the n a vector of A coefficients as a probability mass function where it's normalized in the sense that the sum of the magnitudes of the A sub J squareds is going to have to sum to 1 because those are going to correspond to the probabilities of measuring the system in a given configuration. So what we can do is we can visualize these qubit states geometrically. So what this is called the block sphere. This is just a handy tool for visualizing the state of a single qubit. So this is a state that just is a single qubit. And at this point, we can talk about, we've talked about what is a qubit. A qubit is simply a two-level quantum system. So what the quantumness does is it tells us that we can actually have a simultaneous superposition of the state in multiple possible states. So it's not just going to be in state 0 or state 1, like a classical bit would be, but in fact, it can be in any linear combination of these state 0 and state 1s. Up to a complex phase as well. So what this means is, as you can see in this coding where we have psi is equal to cosine of theta over 2 times 0, plus e to the I phi times sine of theta over 2 times 1. This is just the linear combination where we're in some superposition of state 0 and state 1 with a phase factor. What this does is it maps us to some point on the surface of the block sphere. So a single qubit, the state of that qubit can be represented as any point on the surface of this block sphere. So this kind of shows us, some of the computational power that a single qubit can have is that even with one qubit, one of the basic computational units of quantum computing, there's already this larger than just 0, 1 state space. It's going to be the entire surface of this unit sphere. And we'll come back to this potentially a little bit later when we talk about QAOA, because when we talk about quantum computers, the idea is that we have to manipulate the states of these qubits in order to get them to solve problems that we're interested in solving. So in this sense, oftentimes when we talk about quantum gates, which are the analogs of logic gates in classical computers, a lot of times, a lot of the gates will do things that are geometrically understandable in the sense of rotations on this block sphere. So you can rotate about the z-axis, rotate about the y-axis, rotate about the x-axis. All of these are quantum gates that we can implement on a quantum computer. So we can talk now about the quantum state evolution. What a quantum computer does is it just solves the Schrodinger equation. That's all it is. So this is the equation on the top left here is the time-dependent Schrodinger equation, where H is our Hamiltonian of our system. It's just composed of a sum of a kinetic term, which is this negative h bar squared over 2m times the Laplacian squared, plus our potential energy term, which is this v of x term. So the kinetic energy, that's fixed. That's just, that's physics. What we can do is we can manipulate this potential energy v of x. So what a quantum computer actually does on the physical level is it varies this potential energy V in such a way that we can force the quantum state into different states that are helpful in terms of solving a problem that we care about. So the idea is how can we come up with a sequence of quantum gates that are implemented by varying this potential V of x in such a way that we can manipulate these units of information processing in order to leverage the exponential size of quantum systems to work for us to solve problems that we care about. And these plots are just an example of, you have a potential energy function on the left, which is just a very simple Gaussian peak. And on the right, we have a plot of how this state is going to evolve over time under the influence of this potential. As we can see, time is the x-axis. As the quantum state moves to the right in time, it starts moving in time, but once it hits this potential, suddenly you have this tunneling phenomenon where some percentage of probability shows us that the state is going to be reflected back off that potential, but with some probability it's going to continue to pass through it. So this is one phenomenon that can exist in quantum physics. It's just an example of a simple tunneling problem. But yeah, that's the idea. Is how can we influence the evolution of our problem so that at the end of our circuit, when we measure our quantum state, we get the solution to our problem. And this brings up this idea of measurement, which I haven't really talked about yet. We have all of this vast amount of information encoded in our quantum state, this 2 to the n size state vector. But as it turns out, once we measure our states, we don't have that anymore. Upon measurement, our state is going to collapse into just one of the possible configurations, and you're left with just n bits of information after measurement. So what we have to do is we have to say, well, what we're going to do is create a quantum circuit that will prepare a state that we're interested in, and we can repeatedly measure that state, and we can view that as corresponding to sampling from some probability distribution. So a lot of quantum algorithms are based around this idea of using a quantum computer to prepare a state that corresponds to a probability distribution that is difficult to sample from classically. So this is one way that we can get quantum advantage algorithmically using quantum computers. Okay, so let's talk about some existing technology. This is kind of the fun part. There's many ways that we can possibly realize a qubit system. One way is to use superconducting transmons. So in this sense, we've talked about a qubit, and I guess I didn't really specify, but a qubit is just a 2-level quantum system. Oftentimes we'll talk about the spin of an electron or the polarization of a photon, some of these very low-level physics problem systems. But one way that we can actually implement a quantum computer in reality is to take something that's more macroscopic. It's a transmon or a Josephson junction. And if you can take that and it's built out of superconducting material and you supercool that as close to 0 Kelvin as you can get it to behave like a quantum system. So one of the biggest technologies, these are the ones being built by these big international conglomerates, IBM, Amazon, as well as some startups like Rigetti. They're building these superconducting quantum computers that are really, each qubit is just a circuit built out of a superconducting material that's cooled near absolute zero. So what we have in this image, this is often the stereotype people have for what a quantum computer looks like. The quantum computer itself is just a chip. It's a very tiny part of this. Most of what you see here is just the infrastructure for cooling the system in order to get that superconducting stuff to happen so that we can actually have these quantum properties exhibited. So that's one way. Another way is to use what's called a trapped ion system. So these are really cool. And this is more of a low-level physics system because in this case, each individual qubit is literally a single ion, a single ytterbium ion that is trapped in place using a sequence of minute, very precise electromagnetic fields. And then the state of the system is manipulated by using these laser pulses. This is what the blue lights at the top of the image are. Those are lasers that will shine in on each individual ion to subtly change its state in order to carry out the calculations that we care about. So a couple of things here. These are going to be, in general, more accurate. Trapped ion computers are, as a rule, an order of magnitude more accurate than transmon quantum computers. They also have the advantage of full connectivity. What this means is you can get one qubit to entangle with any other qubit in the system because you can physically move the ions around in this chip. So using these electromagnetic fields, you can actually move the ions in position. So where they actually are, and I'm pointing, it's in this little line right here. The ions are going to be in there in just a straight line. But you can make them switch positions with each other, shuttle them around however you want in order to realize the connections that you need. In contrast, transmons, it's baked onto the chip. So you're stuck with much lower connectivity, which results in deeper circuits and therefore lower fidelity in your results. So there's some big advantages to trapped ions. Some of the shortcomings is it's hard to scale them, so far at least. Trapped ion machines have been built up to maybe 100 qubits. That's like at the highest end, whereas in terms of transmon superconducting quantum computers, those have been realized up to 500 qubits, and that was a couple years ago. They're working on 1,001 now, with the goal for millions by the end of the decade. So there's a lot of hope for scaling these transmon-based devices higher than we currently are able to do with the trapped ion machine. Another option is to use a neutral atom array. This is a little bit similar to the trapped ion machine in the sense that each individual qubit is a single atom. These are realized using arrays of what are called Rydberg atoms. These are really cool because they use what's called a pooling laser, where you arrest the momentum of an atom in space by hitting it with a laser in order to stop it and hold it still. And when you can do this, you can create these just lattices of Rydberg atoms together. And the advantage is these also will have high connectivity because you can move the atoms around on the chip as well, again, using these very precise cooling lasers. And there's also some other advantages in terms of multi-species qubits this is more technical than we'll get into here. But there's a lot of hope. This is more of an emergent one that's, I think, gained traction recently. And also is just very cool on a physics level. And finally, we have photonics. This is actually what I am currently working in. It's kind of a different paradigm of quantum computing as well that we won't talk about today. But the idea here is that you can visualize a quantum state that's composed of the photons that exist inside of a waveguide. And then using these basic optical elements, beam splitters, interferometers, you can cause these photons to interact in such a way that you can manipulate the state of a quantum system. An advantage of this is it's super scalable. It's very apt for representing continuous variable systems because it is an underlying continuous system that you're dealing with. So it's also very scalable. You can put a lot of waveguides together into a big system. One of the downsides is it's a little bit harder to get things to interact with each other. So this is kind of just on the physics level, an example of some ways that we can implement a quantum computer. What we'll talk about for the rest of today, though, is going to be agnostic to all of this. The idea is these are all possible implementations, but we're going to go a little bit higher up in the abstraction level. We're going to climb the stack up to the point where we're just coding up general algorithms that could be implemented in theory on any of these types of devices. So as our first example, we're going to talk about Bell states. This is going to be our demo. So this is the last slide before we get into some code. The basic idea of a Bell state is we have a 2-qubit system, which means that we have 4 possible pure states. So we could have, upon measurement, either a state that is 0, 0, 0, 1, 1, 0, or 1, 1. So these are the 4 possible states for a 2-qubit system. What a Bell state is to manipulate the system to place it into the following state, where we have a 1 over square root of 2 times 0, 0, plus 1 over square root of 2 times 1, 1. So a couple of interesting things we can double check. If we take those amplitudes, these 1 over square root of 2, if you take the sum of those squared, it's going to be 1/2 plus 1/2 equals 1. So the probability is going to match up. This is a valid quantum state. But the interesting thing about this state is that it is not factorizable. And we'll talk about that in a minute. So again, equal probability. So what this means is we take this state that is in this state, we measure the system, we're going to get either a 0, 0 or a 1, 1. And we get those with equal probability one way or the other. So the interesting thing here is that the Bell state cannot be factored. And this is the basis of the EPR paradox. This is due to Einstein, Podolsky, and Rosen. And it was a big thing that was used to argue actually against quantum mechanics back a century ago. But the idea being, say that we measure 1 qubit and 1 qubit only. We measure qubit, the one in the first register, and we measure a 0. We know with certainty that the state of the other qubit has to also be 0, because there is no probability of measuring the state 0, 1. So we measure the state of the first qubit and find a 0. We know that the other qubit has to be in state 0 as well. Now this is going to hold regardless of the distance between the qubits. You can put the qubits into this state and then separate them an arbitrarily long distance. And assuming that the quantum state maintains isolated from any other environmental factors, you will be able to know something about the state of the second qubit, even if it is, in theory, light years away. This is going to violate a lot of the rules of physics that as we understood them before quantum mechanics. This is information being transmitted faster than the speed of light. And this is why it's the basis for the EPR paradox. This is something that on the physics level you can try to come to terms with. It's also a very useful thing that we can do as almost a hello world type thing for quantum computing. Can we create create a Bell state and measure it and see if our measurements are actually working out properly? As a side note, this is also important for a phenomenon called quantum teleportation, which is important for some of the not quantum computing necessarily, but quantum communication type stuff. So if you've ever heard of something like quantum key distribution, or this idea of quantum cryptography, where you encode some information so that an adversary can't access it, not because they can't break some level of encryption, but because the laws of physics make it so that they literally, without the right key, cannot access that information. This is the basis of some of those types of technologies. And it can also be used in quantum computing as well, in terms of, highways on quantum chips. And we won't get into that. But the idea is, let's go ahead and do a demo using Qiskit to prepare and measure the Bell state. So this is going to be our first Jupyter notebook here. let's talk a little bit about Qiskit. Qiskit is just a Python package. You can install it in any, Anaconda environment or however you use Python. You just do pip install Qiskit. Now, Qiskit is a coding language. It's a Python package that allows you to write instructions for quantum circuits. This allows us to simulate quantum circuits. They have some simulation backgrounds, but it also allows us to implement code on real-life quantum computers. This language is developed by IBM. This is their implementation. There's a lot of different companies that make their own languages for their own quantum computers. This is probably, in my understanding, this is the biggest one, and it can also be used for other companies' quantum computers as well. They kind of have to make it work because this one is so ubiquitous, but this is the language that IBM has developed to talk to quantum computers and also simulate them. So we could use the code that we'll do today to actually code and run it on a real quantum computer. And IBM does have some publicly accessible quantum computers. You just have to connect an account. There are some free ones if you want to play around with it. You can use this exact code with a few extra lines to link with the account. But we can also use it to simulate. So all we're going to be doing today is simulating what a quantum computer would do, and we can run these simulations just on our laptop because we'll keep it relatively simple, small level systems. You can always simulate them, with this exponential overhead because you are simulating this massive, exponentially large quantum system. Okay, so I guess I'll just go through stuff I sell. I'm assuming that anyone, following along has the Jupyter Notebook available as well. We're just importing packages here, some basic standard library ones, as well as these three that come from Qiskit, which is just a visualization package that we'll use to plot some histograms, our simulator, which is what we're going to use to simulate our quantum state, and this quantum circuit function, this quantum circuit class, which is just will instantiate quantum circuits using this class. Okay, so I'm in the wrong demo, actually. It's the same. There's some extra packages in that one. I was in the wrong tab. I saw QAOA in the next tab, and we're actually not doing that. We're doing this one. Sorry. It's the same introduction, actually, so my bad. Not QAOA, we're doing Bell State. We'll do QAOA next. But yeah, all the same stuff, the same Qiskit packages that we import. Okay, so in this demo, we're just going to construct a quantum circuit to prepare and measure the Bell state. And, there's actually 4 different Bell states. We're going to do this one. It's the first one. Okay, so let's go ahead and import our packages.
So there's 4 different Bell states that are possible, or like that are in this cell right now?
That are possible. So you can think about each of these 1 over square root of 2's could be positive or negative.
4 combinations of 1s and 0.
Okay. Yep, and there could be a complex phase in there as well.
Okay.
Yeah. So yeah, but we're going to focus just on this state, which is just your generic. This is what people think about Bell state. Okay, so what we're doing here is we're just going to, this is just setting a variable. This is just an integer variable, n qubits equals 2. And then we're going to instantiate this circ object. Now this circ is going to be our quantum circuit. And this is, we're just taking this quantum circuit class and we're instantiating it with this n qubits parameter, basically saying I'm going to have a quantum circuit that will have 2 qubits in it. So this is going to be, and we can visualize a circuit with wires coming in and out. This is going to be a 2-wire circuit where each wire is an abstraction for a qubit. And what we do here is circ.h, 0, circ.cx, 0, 1. So these are just quantum gates. This H is going to be a Hadamard gate on qubit 0, and this CX is going to be a controlled NOT gate on control 0, target 1. What we can talk about in terms of quantum gates, mathematically, it's really easy to think about. A quantum gate is just a unitary matrix, orthonormal matrix, depending on the vernacular you're familiar with. But you can just think of these both. This is going to be a 1-qubit gate. So this is a 2x2 matrix. It's just going to be 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2, 1 over square root of 2. Those are the entries. What this will do is prepare kind of an equal superposition state for this first qubit. And by the way, it's always assumed that a quantum state is initialized in the 0 state with all qubits starting in just the 0 state. So this is our Hadamard gate on qubit 0, and then this controlled X is going to do a bit flip on qubit 2, if and only if qubit 1 is in state 1. So that's why we call it a controlled gate. And a controlled NOT gate, we do that bit flip if and only if we have the first qubit, the target qubit the controlled qubit in state 1. And then at the end, we just do this measure all. This is just saying that we're measuring all qubits in the Z basis, kind of the default basis. This is the bit basis. This is just a measure. Okay. Now this is all well and good. It's a simple code, but it's hard to think about what it's actually doing. We can visualize it. I haven't done it yet, so I'll run it. It's not going to do anything yet. What we can do is we can call on quantum circuits draw method to get a visualization of our circuits, which is circ.draw. And this MPL, you don't actually need this, but it will use matplotlib's circuit drawing package. It'll just make it look prettier. Let's run this, and this is what we get. So this is our visualization for a quantum circuit. This is first qubit Q0, second qubit Q1. And this down here, this measurement is just showing that at this end here, we're going to, these two symbols correspond to a measurement in the Z basis, where we measure either a 0 or a 1. So we have an H gate, Hadamard gate, being applied to qubit 0 only, after which we have our controlled NOT gate, which is a 2-qubit gate. Which, you can think of this as a 4x4 matrix that's acting on both qubits. And this is the symbol for a Z-NOT gate. These are kind of these are very common building block type quantum gates that are implemented in the system. Okay. Any questions up to this point? I've kind of been talking for a minute. So active. It's just not many people here, so I've kind of just been plowing through.
Yeah. So, okay, so there's the qubits, and they have different states, but you don't really, when you try to measure the states, then they resolve into something.
Yeah. You go to the whiteboard. It's like if you think about your quantum system, you have like your wires, and these are qubits. So let's take 3 qubits.
Yeah.
This is going to start in the state 0, 0, 0. But then as soon as you start doing stuff, you have some quantum gates here that are doing some sort of thing. This is going to be a 2 to the 3rd state space. It's actually going to be, there's 8 possible states here, even though we only have 3 qubits. So the system, the state, like the phase space that we're acting in here is a dimension of 8 space. But then at the very end, we do our measurements. Once we measure it, we get, maybe 1, 0, 1. And this is, we get, 1, 1, 1, we could get 0, 1, 1. Any of these 8 possible options, we're going to measure only one of these. So we have all of this high dimensional stuff that's happening, but we start and end with only 3 bits.
Okay.
So this is kind of the challenge with quantum computers. The way that we're actually going to do things is we're going to run this a bunch of times. And maybe we get some probability distribution. Maybe we measure 0, 0, 0 with probably 1/8. Maybe we get 0 probability of getting 1, 1, 1, and maybe we have like a 1/4 probability of getting 1, 1, 0, like that kind of thing.
Okay.
This will give us kind of the shape of a distribution on our space that will give us some information about our problem, and we can use this to get a solution. So in reality, we're going to be using much larger numbers of qubits than this. To get quantum advantage, for example, you're going to need hundreds of qubits in your system, for QIO at least, which is one candidate for quantum advantage in these early days. So the probability distribution is going to tell us, like, it's not continuous, but you can think of it as like a histogram of values, and we'll see some of those later in the presentation. That's what you're going to use to try to, glisten some information or glean, I don't know, try to get some information about what's actually happening to the problem.
Okay.
But that's all kind of the abstract stuff. What we're doing here, this is more, the idea here is to ground us a little bit and just say, oh yeah, we're just doing a very basic 2-qubit circuit, and we're going to see what happens, right? And we know what we should have. We should have, when we measure here, we should have, 50% of the time we measure 0, 0, 50% of the time we measure 1, 1, and we should never measure 1, 0 or 0, 1. Okay. Because those are not, like, what this circuit does is prepares us to be in this state. When we get to this dotted line here, this is the quantum state. And like, you can think of the full state vector as being, it's a length 4 state vector. It's going to be 0, 0, 0, 1, 1, 0, 1, 1. Those are our states. And we could draw like a little graph here and say, what's the probability of each state? This is going to be 1/√2 probability angles. So you square these probabilities. Yeah. Okay, 1/√2, 1/√2, 0, 0. So this is our actual Q vector. If that makes sense.
Yeah.
We're just hiding it because we only have 2 states that have non-zero probability.
Okay.
Which is often the case. This is one way that like quantum algorithms can be used, is like, you have this very massive state space that you're exploring, but in the end, once you actually use your quantum circuit in like an efficient way, you shouldn't have to deal with most of that massive state space. You should have
Mm.
isolated down to, you should be able to explore that massive state space, but find the area in that state space that's relevant to your problem. Think about it as like, there should be some lower dimensional manifold within that massive state space that contains good solutions.
Mm.
And your goal is to find an algorithm that can arrive onto that part of the phase space.
Okay, okay.
Okay. Yeah, so this is our circuit. We've only created it. It's just a theoretical object. What we have to do is now try to run it. So a couple of notes. In order to run and simulate runs on this circuit, we have to declare a backend. So this is going to be our simulator backend. In another world, you know, if we linked this with an IBM account, the backend could be one of their quantum computers. But in this case, we're just going to use their air simulator, and specifically, we're going to use a state vector simulator. Excuse me. I have a couple of notes here. In some cases, you can accelerate your compute time in terms of your simulation by using other simulator backends that leverage like tensor networks to more efficiently encode the state. This is only going to work for lower entanglement systems. State vector simulator is the brute force method of actually calculating the 2 to the n state space at every step.
Okay.
So it's going to be exponentially expensive. There's an overhead to simulating this. We can only really do this up to like 30 qubits on laptop. And then as another note, you know, Qiskit does support GPU acceleration. So if we had a GPU, we use that. Certain backends will also support more realistic simulations with noise. So what we're doing here is an ideal simulation, assuming that our system is entirely isolated from the environment, which is not how quantum computers will ever really work. And that's actually one of the big problems with quantum computers in this age, in this like era of quantum computing, is that we're still stuck with these very noisy quantum computers that are very susceptible to making errors based on outside noise. So one thing that we can do, you know, on a scientific level is we can simulate them with that noise baked in, taking like statistics about what the noise would be from real quantum computers. And do like, this would require us to do a more complicated like density matrix representation of our state, which we are not talking about today. It's just there in case you're curious. And then, yeah, this same code, this is the nice thing about Qiskit, and a lot of other coding languages support this as well. But the same code that we're writing here, everything can be used one-to-one to execute this circuit on a real quantum computer through the cloud.
Yeah.
The only additional requirements are one, connecting with an IBM account. That's 1 or 2 lines of code to do that, along with, you know, actually creating an IBM account. And 2, you have to add a call to a transpile function. This is just a compiler level thing. Like, think about, like, we have this set of logical quantum gates, but the physical quantum computer might have not all of those gates. It can implement those gates using a decomposition in terms of the gates that it natively supports. Each quantum computer is going to have different ones. We're a high level of abstraction in the stack here, where all of our code is agnostic to the actual platform. We could run this on any, in theory, any quantum computer that supports this coding language. A transpile function would simply take our code, which is this circuit here, and maybe it would have to add some extra gates in order to, maybe there's not a C0 in practice, which actually on a transpile computer there would not be. And you'd have to get this into a correlated phase gate or something. And so there's going to be some decomposition. It's not going to look exactly like this. That's all the transpile would do. Take our circuit and create an equivalent one that would use only stuff that the hardware would really support. Yeah, that's just a big spiel. We can not spend too much time on that. It's just so you're aware. Let's go ahead and run this though. So we take our backend equals simulator, we just declare our backend here, and then to run it, we say counts is equal to backend.run.result.get counts. So we're in line doing a bunch of different stuff, but basically think about it as backend.run is going to run our circuit and return an object that contains all of the results from that. The dot result is going to get the results, and then the dot get counts is going to take those results and get the specific counts. And this is what we actually care about. So you can see our counts we've measured 0, 0, 49 times and 1, 1, 51 times.
So yours is much more balanced than mine.
What'd you get?
I got 38 and 62.
Oh, interesting.
Yeah, it is interesting.
So let's try something then. I haven't talked yet about this shots parameter. What shots is saying we have this circuit, how many times do we run it and measure it, right? The more shots you take, the more accurate you're going to get. Think about it as sampling more times is going to give you a more robust estimation of your actual underlying distribution. It's also more expensive. You know, if you run this on a real quantum computer, they do charge you by the shot. So it's whatever fraction of a cent per shot that they charge you. So a lot of times optimize, like one of the things that I've been working on in research is taking one of the algorithms we're going to look at today, which is QAOA, and trying to reduce that shot cost to still get an accurate result. Let's add another zero and try it again then.
Yeah,
And
my the 1,000 was much. Oh yeah, it gets closer and closer.
yeah. And by the way, it's always random. Like it's going to be different each time you run this cell. And that's the underlying. There's this underlying probabilistic nature to quantum mechanics where it's always going to be random in some sense.
So in like in a real quantum computer, it's like it is actually random, but it's like this like simulated random.
It's a simulation.
Okay.
Yeah. But yeah, that's actually a cool thing. It's like, well, think about this is actually a coin flip. If you had access to a real quantum computer and you could like get the noise low enough, this could let you do an actually truly random coin flip.
Ooh,
Is what this would actually amount to.
that's cool.
Okay, cool. And then the last thing we're going to do in this demo is we can use this plot histogram function to visualize our results. So we have our two states here, and we'll note that it's not showing any other states because we didn't measure any other states. If we measured more, like, there's other states that just don't exist because there's zero probability of measuring them here. But this is just going to show us the probability. This will look more interesting in the next demo when we talk about the other. And I'll try to rush here because I know we only have about 20 minutes left. I've probably taken too long so far.
No, you're good.
But let's go ahead and move on to the quantum approximate optimization algorithm. So this is our first algorithm. Instead of just doing our hello world level Bell state thing, we're now going to use an actual quantum algorithm, which is something that is designed to run in NISQ era quantum machines. So what this means is eventually the goal is fault tolerance. The goal is to be able to run Shor's algorithm, do the quantum Fourier transform, all of these very expensive high level operations that will actually, be transformative in absolutely like changing the face of what scientific computing looks like. In the near term, we don't have quantum computers that are good enough for that just yet. But the idea of NISQ algorithms, which stands for near-term intermediate scale quantum algorithms, is to say we have these quantum computers now. They're not good enough to do some of the really big boy stuff that we want to deal with, but can we still leverage them to solve problems and maybe get some speed up over classical computing in some way, even with the limited resources we have now? So one candidate for this is called the quantum approximate optimization algorithm. So the way that this algorithm works is we start by preparing two Hamiltonians, HC and HM. It's going to be our cost Hamiltonian and our mixer Hamiltonian. The only things to know about these are the following. The cost Hamiltonian HC, the ground state of HC should encode the solution to our problem. So if we can arrive at the ground state of HC, we can measure and recover the solution to the problem that we care about. The mixer Hamiltonian should not commute with HC. That's a rule. It can't commute with HC. And it should also be easy to prepare the ground state of HM, because the idea is to start in the ground state of HM as our initialization. So we can define this intermediate Hamiltonian, which is just this convex combination of our mixer and cost Hamiltonians. And then there's this idea from physics called adiabatic evolution, where we can take this time evolution operator here, U of H and T. This is just a solution to the time-dependent Schrodinger equation. Basically what this exponential does, this is a unitary operator that will evolve our quantum state for time t under the influence of Hamiltonian H. So what adiabatic evolution tells us is that if we start in the ground state of HM, which is what we're going to visualize, abstractly as this point here, and we move through our phase space very, very slowly, very, very slowly increasing our time using this convex mixture Hamiltonian here, we'll traverse this phase space, and if we are isolated from our outside environment and evolve slowly enough, we are guaranteed that eventually, after a certain amount of time, we will arrive at the ground state of HC. This is a way to actually solve this problem where HM is very simple. We can start in our ground state here. HC might be complicated. It might be an exponentially difficult problem. This could be like the solution to an NP hard problem, which is what we're going to deal with today. But if we can arrive in the ground state of HC, regardless of how we get there, in this case, we can get there through adiabatic evolution, we will have solved our problem. Okay, so let's talk about how we can use a quantum computer to do this. What we're talking about here is simulated adiabatic evolution. So this is something that we could run on a discrete, qubit-based, gate-based quantum computer. What we're doing here is we're taking this trotterization, which simply means that we take this exponential here, e to the negative I h of t, which is this thing here. The difficulty here is that HM and HC do not commute. So this can be difficult to implement directly. In fact, we can't implement it directly. So what we can do is we can approximate this time evolution operator by taking this trotterized approximation formula. What this basically amounts to is repeatedly alternating between applying e to the HM, e to the negative ITHC, right, for different time steps here. And as long as this, we have this divided by n here, we're basically taking very small time steps of under HM and HC back and forth over and over again. If we do this repeatedly For small time steps, what we will end up doing is basically following this adiabatic path approximately through the phase space and still arrive close to our actual solution.
So you just alternate them.
Yep. Now, what QAOA says is maybe this is not feasible to do. You know, this is an example with a few steps. It might be intractable to actually do time steps small enough to get here. In fact, a big issue is maybe we lose coherence of our system by that time and we no longer get accurate results. What QAOA says is, can we find other choices for these gamma and alpha time step parameters so that we can still walk through this parameter space, but maybe we find a more efficient path, but we still arrive at the ground state of HM. And what we can do is use classical optimization techniques with the quantum circuit as essentially our cost or objective function to find these time steps that allow us to still walk through this parameter space, maybe not following the adiabatic path anymore, but using it as a heuristic for saying there should be some set of parameters that I can find that will get me to the ground state of HC and therefore recover the solution to my problem. So the way that we do this is construct the following circuit, and this QAOA circuit is simply going to do this trotterized time evolution operator that we saw in the previous slide. What we do is we initialize our state to an equal superposition state, basically no information in this state. Every state in our phase space is equally likely to be sampled as any other state. And what we can do is we construct parameterized circuits that are just time evolution operators for HC and HM separately. We alternately apply them n times, where n is our number of layers in our QAOA circuit. And what we can do is we can vary these time evolution parameters, these time steps, gamma and alpha, for each layer. So what we can do is we can optimize gamma and alpha using a classical algorithm, you know, anything in SciPy we can use. And if we can optimize these parameters running this quantum circuit multiple times over and over again, the goal is to say, I can find these parameters in order to find my solution. So in a big picture sense, what we're doing here is we have this very large dimensional phase space that we're working in. So you have 30 qubits, that's a 2 to the 30 size phase space, which is very, very big. But what we're doing is we're parameterizing our phase space with a very small number of parameters. So the QAOA circuit is living in this very high dimensional world, and it's exploring that high dimensional space, but it's parameterized by a very small number of parameters that we can tweak, you know, efficiently using classical algorithms. So let's actually do it now. Let's go back to our Jupyter notebook and click over to the QAOA demo. This one's a bit longer, so we may not have time to go super in depth with all this, but we'll at least run it and get some results. And the notebook's there if you want to play around with it later if you're interested. Okay, so again, we can import our packages and we can go ahead and start talking about it. So in this demo, we're going to implement QAOA, the quantum approximate optimization algorithm. We're going to use it to solve a max cut problem. Now, if you haven't heard of max cut is just a prototypical NP hard problem. And it doesn't really matter, you know, if you can solve one NP hard problem, you can solve all of the other ones. They're all efficient under the unique, or they're all equivalent under the unique gains conjecture. So basically, if you can find an efficient solver for max cut, you have an efficient solver for all of your NP hard, you know, minimum vertex cover, knapsack problem, traveling salesman, all of these can be solved. You know, if you can solve one, you can solve the rest. What we're talking about today is max cut, which basically says we're going to take a graph, and I'll clear our output so we can run it all together, actually. Take a graph and we basically say, I want to find a bipartition on that graph, you know, basically two partitions with the maximum total weight possible going between the two partitions. Okay, so what this does is this is just, you know, boilerplate network X code for creating a graph that's just going to be our example. We'll come back and do a slightly more complicated one later, and you can play around with whatever you want, you know, if you're interested in changing the structure of the graph. But we'll do an easy one, just a 4-node graph with kind of this square structure. I guess it's a rhombus. Never thought you'd use a rhombus after junior high. There it is.
So the goal is for them and the problem to find. So like the max cut would probably be through 3 and 2.
The max cut would actually be through all of the edges. You could draw.
Oh, okay.
Think about it as you put 0 and 2 in one partition, 1 and 3 in the other, and then your partition is gonna go around and cut.
Okay.
Yeah, and in general, that you can think about max cut like visualizing it. You can have any line that goes through and cuts the edges, but it can only cut each edge once, and it has to start from going outside of the graph and end going outside the graph.
Gotcha.
Okay. So this is our graph. What we can do, and this is going to be in my. I'll go ahead and pull it up. I have this helper functions.py. I've put just a naive exact solver here. This just goes through all possible cuts. and says which one has the largest cut value, right? 0, 0, 0, 1, 0, 0, 1, 1. Like we check all of them and see which one has the highest cut value. So that's what this is doing right here. And we'll go ahead and print the result. It turns out that 0, 1, 0, 1 is our optimal partition. And this is going to have a cut value of -7, which you'll notice is the sum of all of the nodes. And by the way, it's negative here. This is just an artifact of SciPy's functions are for minimization. So we just multiply everything by -1 to convert a maximization problem into a minimization problem. So it's standing stuff. Okay, so as a quick note here as well, this is one possible option. You'll note that the same cut value would be achieved by getting 1, 0, 1, 0. It doesn't actually matter, how we label the partitions, zeros, ones. As long as they are, that's why it's binary. It doesn't actually matter which one corresponds to which. Okay, so now let's construct a QAOA circuit that will solve the max cut problem. So to begin, we're going to do our cost layer and our mix layer. And really what these are, if we're being pedantic, is functions that will add a mix layer, add a cost layer to a quantum circuit that we pass in as a parameter here, circuit. And we'll notice we have these beta and alpha here. These are the parameters that we're going to allow to be used for that layer. These correspond to the time step for that specific layer. Okay. Oh, and we're also basically initializing n qubits to be the number of nodes in the graph. For QAOA, for a graph of 4 nodes, we're going to require 4 qubits. It's always going to be the case. Okay. So the mixer layer is very, very simple. All we're doing is this rotation X gate. And the rotation X gate is going to be, we're going to run through every qubit, and each qubit gets a rotation X gate placed upon it. And the parameter is 2 times beta, 2 times that time step. Okay. Cross layer is a little bit more complicated. What we do here is we first just get the weights in our graph, and then we walk through every single edge in the graph, and we add this. This is called a double Z gate. It's implemented using 1 rotation Z and 2 controlled X's. And the X's the controlled gates are nested around the rotation Z. So we just define our control and our target as the pair that's corresponding to the nodes attached by this edge. And we just place a controlled X gate on the control and target, a rotation Z gate on the target, with the parameters going to be alpha, our time step, and we're actually going to multiply the weight of our graph. This is like the slightly more complicated version of this algorithm. If you wanted to do max cut for a non-weighted graph, all of these weights would just be 1, and it would reduce to just being alpha, just that time stepping, the length of the time step parameter. And then we do another controlled X gate. So this is how we would define this is how we would define a double Z gate, a double Z rotation gate, and that's all we're doing here. Okay, so these are our cost and mixer layers. These are time evolution operators that correspond to time evolution under our cost and mixer Hamiltonians. So it's kind of abstracted away here because we've not actually written down a closed form for our cost Hamiltonian. We could, it's just like a sum of 1 minus double Z. I haven't really done it here, and that's perhaps an oversight. You can find it online if you Google. I followed along with a lot of tutorials for quantum computing stuff. We'll do QAOA as a basic example. Okay. So you can find plenty of resources online. Penny Lane has some really good ones. What we're doing here is time evolution under that Hamiltonian. But if we can get to the ground state of that Hamiltonian where this is the time evolution operator for it, again, we've solved our max cut problem. So that's kind of hidden away in this step, but we implemented the time evolution operator for that Hamiltonian, which is all we actually need a closed form for anyways. Okay, so now we get into some of the more complicated stuff. So what we're going to do here is define a function that will construct and return our QAOA circuit by repeatedly calling our cost and mixer subcircuit functions that we defined up here. So as a note, this is going to admit parameters alpha j and beta j that are going to vary, could be potentially different for each layer. So this whole thing is going to be parameterized by a vector of alphas and a vector of betas, or a list, because we're in Python. So, so the way that we do this, we define our number of layers, n layers. And this is just going to be the length of either of these. I take alphas because it's first, but it's these alphas and betas will be the same length. We pick either or. And then we do here, what we do here is we just define circ. We just initialize a quantum circuit with the same number of qubits as nodes in our graph. We set this parameter earlier. And then we are going to do, like I said earlier, we initialize every single qubit in the equal superposition state by calling a Hadamard gate on every single qubit. And then what this step here does And these barriers are just for visualization later. You can ignore those. They don't actually do anything logically. They're just to draw our circuit nicely. But we have add cost layer, add mixer layer, and we do that in a for loop over all of the number of layers. We add our measurement and we return our circuit object.
But you said what did you say about the barriers?
They're just for visualization.
Okay.
We'll see that in the next step. You can ignore them. They don't do anything logically, but they are there. So I just wanted to make sure I don't skip over it. So let's go ahead and run our construct circuit function. And I'm just passing in these alphas and betas. I'm basically just passing in one as a stand-in, but we're basically saying, let's make a 2-layer circuit. So like 2 time parameters for cost and mixer layer respectively. That's what this is doing right here. And we just do our circ.draw to see what it looks like. So we can see here, this is our Hadamard layer. This is just initializing using Hadamard gates. This is what one of the barriers does. It just, I'm basically adding a visual layer between our initialization, our cost layer, and our mixer layer. So this right here, this is our cost layer. This is time evolution under our cost Hamiltonian. So you can see our double Z gates that are implemented using C naughts and rotation Zs. And we just have those over all of the possible edges. So this is going to be specific to the graph. This is where the graph structure is encoded in our circuit is through this cost layer. And then this right here, this is our mixer layer. It's a lot simpler. It's just rotation X's on each qubit, no entanglement even happening here because there's no 2 qubit gates. And then it's just repeated. So we have another cost layer and another mixer layer because we did a 2-layer circuit. So in practice, we could have, whatever, that's a parameter. We could repeat these as many times as we want. And there's, this is kind of a machine learning type problem where that's a hyperparameter that we could tweak when we try to optimize the robustness of our algorithm. And then we have our measurement step here after all of the layers. Okay, so we have code that will create a quantum circuit for us. The next step is to set up our optimization. So this is where we say we have all of these these time parameters for each layer, our alphas and our betas. Let's figure out how we optimize those. So what we're doing first is we're saying, given a bit string X, where X is going to be, in this case, 111, 1, 0, 1, 0, 1, whatever it is, we're going to get the cut value of that. And I'm not going to go too in depth here. It's kind of a messy way of describing it. It just happens to be a little bit faster than doing it using for loops. That's all this function does, is get the cut value of a bit string X. And you'll notice that if we change our graph, it'll change this function as well. We could recall the graph. Okay, so we have that in place. Great. Once we've got our objective function, this will get us our cut value. We now have to do a subroutine that'll execute our QAOA circuit for a given set of alpha and beta parameters and with a predetermined number of shots. And then we're going to get from that the average value cut across all of the measured bit strings that we get. So we run our circuit with a given set of alphas and betas. We measure it a bunch of times, and we get for each of those measurements, each measurement is going to be a bit string that corresponds to a cut for our graph. For each one of those, we're going to get the cut value using this function that we defined up here. We get the cut value for each of those and then find the average cut value from this run of the quantum circuit over all of the measurements that we took. This average value cut across our circuit measurement, this is the objective function that we pass to the classical optimizer. So think about this as like, we have some black box, which is our quantum circuit. This is our function that, like, if you run our optimizer for 10 function evals, that's going to be 10 executions of our quantum circuit with however many shots for each one of those executions.
Mm-hmm. So you get expensive fast.
Sure does. So, but that's all this is doing. So let's go ahead and talk about what we do. We also initialize our backend at this step because why not? Same one as we used before, just using our state vector simulator. And then we have this function that is estimate circuit expectation. So this is just estimating the average value of our circuit by taking a certain number of shots and getting the average cut value across each of those measured shots. So all we're doing here is we set our number of layers to be, the length of the parameters. By the way, just because of the way SciPy works, we combine our alphas and betas into a single params vector. This just splits them into alphas and betas separately. So that's all we're doing here. And then this circ is going to use the function that we defined before to actually construct our circuit in line here. So we construct our circuit and then we run our circuit with shots is the parameter that we defined here. Just putting it down here. And we do our dot result dot get counts. So we have our counts from a single run of our quantum circuit, a single execution of our quantum circuit with, in this case, I've set the default to be 1024 shots. And then all of this is doing is we set our expectation, we initialize it to 0. And then we walk through every single bit string that we measured in our counts dictionary. And we get the cut value for each bit string. And then we add to that expectation the cut value multiplied by the number of times that bit string was measured. And then we return that divided by the number of shots. This is getting an average. That's all it's doing. Any questions up to here, by the way?
I did have a question. So the rotation circuit parts, they change like so there's like in the bit, there's like one part before the bar and then the bits afterwards. And those the rotation changes that beginning part of the.
Yeah, if we go back to our block sphere, that's probably the easiest way to show this. Think about this block sphere is going to correspond to each qubit. It's initialized up at this north pole in the state 0. But if we call, say, a rotation x gate, which is what our mixer layer does, rotation x, say, with the parameter pi.
Yeah.
Oh, what it's doing is saying we take a rotation about our x-axis, so it's going to take a state that starts in 0, rotate by pi. Let's
gotcha.
And then we rotate it here, and now we do a z rotation. That's going to rotate it around this axis.
So and then the amount of the rotation, is it always like is it like it depend? Is like a.
Yeah, that's where we can have our, that's what the time, this is where it gets a little bit tricky, but you can visualize the length of our time step, because those are used as the parameters for rotation gates. You don't even have to think about them as time steps anymore. You can think about them as rotation angles.
Oh, okay.
So alphas and betas, I've been calling them time steps. At this point, having gone past the adiabatic stuff, because that's just the heuristic that QAOA is based on, it's actually probably easier to think about our alphas and our betas as just rotation angles being used. So the betas are going to be rotation angles about the x-axis, and the alphas are going to be rotation angles about the z-axis.
Okay.
And then, there's this added layer of C naughts that's going to move us away from this and makes it harder to visualize, because that's where we get entanglement from, where we're no longer described by qubits on their own block spheres. But the visualization here is still helpful to understand what the single qubit rotation gates are doing.
Definitely.
Cool. Okay, so yes. Any other questions? Cool. Okay, so up to here, we've now got this is our objective function that basically takes our quantum circuit, runs it a bunch of times, and gets the average cut value across all of the measured bit strings that we get out of our quantum circuit. The only thing left to do is to choose an optimizer and use it to find alpha and beta parameters that maximize the expected value cut from our circuit. So I think I've got to run everything. Can't remember if I've run stuff yet. So let's go ahead and make sure that we run everything. And then what we're doing is we fix our layers. We'll use 6 layers in this case, so 6 repetitions of our cost and mixer Hamiltonian circuits. Our initial params, we just choose to be small random numbers. And then this is just calling our scipy minimize function. So we imported this at the top. This is just scipy.optimize.minimize. So very basic, minimize function. And the objective function is just this estimate circuit expectation that we defined up here. Initial params, just this vector of small random numbers. And we're using this method called BLA. This stands for constrained optimization by linear approximation. We don't need to use this, but the reason we do is because this is what we call a gradient-free optimization.
I was say, how do you get gradients for this system?
There's an extensive literature about finding gradients of quantum circuits.
Okay.
We're not getting into that at all here. We're going to use the gradient-free method, which basically just think about it as like a grid search type thing.
Oh, okay.
It's an efficient way of doing grid search where it'll take linear approximations at each step and use the information about what it's searched so far it's a complicated thing. It's due to a guy named Powell, I think. But yeah, all we need to know is it's a gradient-free method that will try to optimize everything without knowing anything about the gradient.
Interesting.
Yes. And then, so let's go ahead and run it. Which will take a second, because each time we evaluate this cost function, and it did it 130 times, this means that we ran our quantum circuit 130 times. Each of those 130 times actually did 1024 shots of our quantum circuit. So we actually did a lot of computations just in those 2.1 seconds right there. But we optimization, it terminated successfully. This is the function value. So this is the average cut. We'll remember that the actual true cut value is 7. Right. Yep. Our average across all of our measurements of our final optimized circuit is going to be -5.7, which is fine because we don't actually need the average to be perfect, because remember, this is sampling from a probability distribution. And each time we vary those alpha and beta parameters, what we're doing is we're changing the shape of that probability distribution. By the end of this optimization process, all we care about is hopefully having moved this distribution in such a way that with high probability, we sample good cuts, high value cuts. And then these, by the way, if you're interested, this is what our final alpha and beta parameters look like. That's all it is. And yeah, let's go ahead and talk some more. Once this optimization step is finished, we simply run our circuit one more time using the optimized parameters, and the highest valued measured cut is taken as the output of our QAOA routine. And then for small graph sizes, we can check this QAOA solution against the exact solution that we already found by naively testing all possible cuts. So let's do that. And I've got some print statements here that'll just give us some stuff. And all this, I won't go too much into the code. This is just walking through all of our measured results from our circuit that was run using those found optimal gamma, those optimal alpha and beta parameters, and it just finds what the best cut is. This is just a simple, walk through a dictionary and find the highest value in it and the corresponding key. So you can see our true solution 0101, our QAOA solution 0101. And by the way, I've also plotted the QAOA mode. This is the most often sampled cut from our QAOA circuit. And it's also 0101, which is a good sign that our circuit is doing a good job. All of the objective function values, I've gotten rid of the negative here. They're all 7, which is great. So what we can do, let's actually plot our counts. And this is going to give us everything that we measured. So you'll notice that we measured a bunch of different stuff, a bunch of different bit strings, a bunch of different possible cuts. But you'll notice that 0101 was measured the most times, and the equivalent 1010 was the second place solution. And then we also have some garbage in here that was measured sometimes, but that's okay.
Interesting.
It's all probabilistic, and as long as we, with high probability, measure the correct solution, we are happy. This was for a very simple example. I will give a 2-minute spiel on sometimes QAOA doesn't do a good job. For example, say there's a big gap between the ground state of our cost Hamiltonian and the ground state of our mixer Hamiltonian. QAOA can really struggle to converge to a good solution in those cases. It can get stuck in local minima. It can do a bad job of exploring the state space. There are ways that we can accelerate the convergence of QAOA. One of them is called warm starting, which is one thing that my research has been based on. What warm starting does is basically says, we're trying to solve this NP hard max cut problem, right? What if we can solve a easier version of that problem? We call that a relaxation. So something that is easier to deal with, that gives us an approximate solution, but is not as hard as the max cut problem. Usually this takes what max cut is, which is a discrete problem where the possible solutions are binary. And it says, let's allow continuous variables instead. And you can use that to find an approximate solution. And then we can use that to adjust our QAOA circuit to encode that information. Think about it as instead of starting from that equal superposition state where every possible solution is equally likely, we say, well, that's kind of garbage because maybe I know that there's some solutions that are probably going to be more likely. I can encode that information that I already know from the relaxed problem into the starting point of my quantum circuit. And this can basically close the gap between those two ground states. So what this really corresponds to is using this relaxed solution to adjust the initial state. So if we're not doing Hadamard gates anymore, we're encoding the initial state using the relaxed solution, and also adjusting the structure of the mixer Hamiltonian. So by adjusting that initial state in mixer, we can increase the convergence speed of QAOA. So these are some simulated runs that I've done using a couple of different warm starting methods. The red one was the one that we were proposing in our research. And you can see in this top graph, this is the best measured cut across all of them. So the blue is standard QAOA. It never achieves a maximum cut for this problem. This is, by the way, a very hard problem. It's max cut for a large, fully connected graph. So QAOA, it's not bad. It's getting this is a percentage of the maximum cut. So it's getting up to 98, 99% accuracy, but it's not getting maximum cuts. And it's got a lot of garbage in there. Whereas all of these warm started algorithms, the distribution of solutions is centered near higher value cuts, and it also achieves more maximum cuts.
And so for the red one, it's like it has its highest counts at the maximum solution.
Yeah. And this bottom graph, this is actually an analog to the histogram that we just were looking at in the notebook, where it's not really, it's hard to, this is like this is over 100 different runs This is the best measured cut, so what we think is the solution. This is the circuit expectation. So this is the actual objective function that we're using.
Okay.
So this is the average across all of the measured cuts. So of course it's going to be lower because we have more garbage mixed in. It's not the best measured cut, it's the average cut that the circuit produces. But again, we see that the normal QAOA circuit is centered much lower around the garbage solutions, around 80% accuracy. Whereas even though we're not, of course, centered around 100% accuracy, because that's relatively unreasonable to expect, our warm starting methods, and especially this one, which is the one we were proposing, has a much better looking distribution where the shape of it you can see is centered around above 90%. So this means that we're more likely to sample a good solution. So as a note here, shots is really important. If we take enough shots, you can take 1 million shots and eventually sample the maximum cut no matter what you use, right? Because it's sampling from a probability distribution. Like, say your distribution looks like this, your perfect solution's over here. It's not a zero probability, even with a garbage circuit that has nothing to do with your problem, you'll eventually sample it.
Right.
The idea is to do this with not that many shots required, right?
Yeah.
So by creating these distributions where the probability distribution that the quantum state corresponds to is centered around high value cuts, you can take fewer shots of your circuit, less expensive,
right,
to get the solution that you're looking for. So that's the idea.
Wow.
Yeah, and that's it. Thanks.
Yeah, thank you.
If you have questions, keep going. But that's the quick demo on QAOA. And sorry.
No worries, no worries. Yeah. Thank you for that.